Hello everyone, am I audible?
Yes, ma'am.
Okay, thank you. Let's wait for some 5 to 6 minutes. After that, we'll start for week 4.
Yes, ma'am.
Okay. All right, am I audible? Let's start the session. Good evening, everyone. So, welcome you all in the week 4 of the course Introduction to Machine Learning, instructed by Professor Balaraman Ravindran from IIT Madras. So, am I audible?
Yes, ma'am.
Okay.
Yes, ma'am.
Okay, let's start. So basically now in this week we will be learning about perceptron and support vector machine, and we have started the basis of these two topics in the last week. All right, we have started with the introduction to machine learning, then we have learned about linear regression properly, then after that we have gone with linear classification. All right, so these perceptron and support vector machine are the type of linear classifiers. So we'll start with some recap of the last week and then connect with this topic. So let's start with introduction to linear classifiers. So as mentioned in the last week, you all know now a linear classifier is a model that makes prediction based on a linear function on input features. So basically I'm saying that classifier particularly is the algorithm which helps you to classify the data, right? So it means there will be some number of classes, and a linear classifier is a model which helps you to classify the data through a linear hyperplane. So basically in the last session we have discussed there are two basic approaches irrespective of regression converting to classification. First is discriminant function approach, in which we define a decision boundary based on the comparison of discriminant function, right? What we have seen, let's say we have some data, right? मान लेते हैं, let's say this is class 1 and this is class 2. So let's have some discriminant function delta 1 for this class and delta 2 of this class, and using some discriminant approach we'll learn a classifier which helps to classify this class 1 and class 2, right? Second approach was direct modeling of the separating hyperplane. What we will be learning here right now, that we need to have this boundary, and how to get this boundary. Now in this session we will be seeing how to direct model this hyperplane. All right, so we will explicitly model the decision boundary which is known as hyperplane here. So an example is given to you for binary classification, the email is spam or not based on the word frequency. It's an example of a classification application. So now here we are going to see how to model this hyperplane, right? So let's start with what is hyperplane first. So as already, this is also we have discussed in the last session class, that hyperplane is the decision boundary, right? As you can see from this figure, the first figure is a R2 plane in which the hyperplane is in the form of a line. The second figure is a 3D plane in which you can see the plane is in the form of a 2D plane, right? The hyperplane is a 2D plane. That's why we can't say the decision boundary is a simple line, and we termed it as hyperplane, which is associated with any dimension of vectors. Okay, so what we wanted to learn this plane, how to get the boundary, how to get this plane. So this plane is defined by a function that is beta transpose x is equal to 0. So this beta transpose x is the same as we are learning in linear classifiers, as we have learned in linear regression also. Okay, and this 0 means the boundary. So if the function is your beta transpose x. Beta transpose x is simple function. If its value is greater than 0, then it will be class 1. If it is less than 0, then it is class 2. And this is, I think you all have done in around 11th, 12th standard, where we use some geometry to say whether the area is above the line or below the line. Okay, so it means that let's say if the function value is greater than 0, it may be in this direction, or less than 0 is maybe in this direction, and on this line it is equal to 0, and I want to find this line. All right, so we have seen two models were there using a discriminant function, and other is direct modeling. So direct modeling, you can see that why only this line is considered to be as the hyperplane. There can be multiple lines. All right, let us say this line can also separate the data. Even this line can also separate the data. So there can be multiple lines here, but how to model the perfect line is our main goal. So first we will be seeing how perceptron algorithm work, then we will go towards support vector machine. So perceptron learning is simple, how to create this line, how to create this boundary, so that our data can be simply accurately classified. Then there are some drawbacks of this perceptron networks, and we'll move towards the more appropriate, or you can say popular model, that is support vector machines. Okay, so obviously this hyperplane, as you have learned geometry in your lower schools, or in your courses, there are some properties of lines, let's say curves. Similarly, there are some properties that should be satisfied to say that this particular plane is a hyperplane. Okay, so these properties, just look here carefully. This is a simple 2D area in which a line is created, and this is called hyperplane, as it is mentioned here. Okay, 2x plus y minus 3 is equal to 0. It means here what we mean by it, that we have a vector, look, this 2x plus y minus 3 is equal to 0. So this 2 and 1 are your beta vectors. Remember, we have two things in beta, beta naught plus beta 1 x1 plus beta 2 x2, and so on, is equal to 0, right? Here x1 is denoted as x and x2 is denoted as y. So basically we are in two-dimensional space in which some points will be classified as +1 or -1, or you can say two class classifier, and in which there will be three hyperparameters or three weights which we have to model, right? In linear regression also we use this concept. So here beta naught is a separate thing. Beta 1 is associated to x and beta 2 is associated to y. That's why I am saying this 2 and 1 are the values of beta 1 is equal to 2, beta 2 is equal to 1, and beta naught, can you write the value of beta naught from this line? What is the value of beta naught?
Ma'am, -3.
Very good, right? So
Minus 3.
we have these values of beta, right? So now we are defining some properties of hyperplane. Okay, so just look here. Let me remove all this. So now you get this, right? What is beta here? All right. So let's say there are 2 points. So what I am saying, just look at the first point which is written here. Let x1 and x2 belong to the hyperplane L. So wherever I am going to use the hyperplane, I will name it as capital L. So let's say there are 2 points. This is x1 and this is x2. Okay. And these x1 and x2 are vectors. So how the vectors look like? This. Is that clear? Is there any problem in this representation? I am saying, listen again, this x1 and x2 are 2 points which are lying on this hyperplane. It means these x1 and x2 are on this line, and I am saying that this x1 and x2 are two vectors. So how the vectors look like? In this form. Is it clear? Any
Ma'am,
problem?
Ma'am,
Okay.
form, ma'am?
is
Okay.
hyperplane.
Sorry, any doubt?
Ma'am, why?
Ma'am, which form, ma'am?
This form, this I have joined the line from origin to this point x1. Can you see these two lines?
Yes, ma'am. Yes.
Okay, so the third line is normal vector which is written. What I'm saying, these are 2 points. Okay, these are 2 points on line, so these are not just 2 points, these are vectors. So vectors are considered when they are connected with the origin. Okay, so
Ma'am,
these
why
are two.
we explain as hyperplane, ma'am?
Sorry.
Ma'am, why we call this plane as hyperplane, ma'am?
Sorry, I didn't get it. Again, please. What
Ma'am,
is
why?
hyperplane?
Yes, ma'am. Yes, ma'am.
Okay, I am saying, let's say hyperplane means the decision boundary which separates your classes. Let's say there are some classes. So let's say there are this class, some points are here and some points are here. Okay, so this line will separate these 2 points. So I am saying, I am giving you, this is already given to you, that this is a hyperplane, let's say, because I am defining the properties of hyperplane. So it should be that the hyperplane should be given to us. Okay, so this line, this blue colored line is your hyperplane L. And the equation of line is given here, 2x plus y minus 3 is equal to 0, in which I have given you the values of beta and beta naught. Is that clear?
So,
In
ma'am,
this, hmm, yes, go on.
the line 2x plus y minus 3 is this blue line.
This blue line, right?
Or and the x1, x2, your mark on line, this are factor x1, x2.
Yes, I'm saying x1 and
And
x2 are two any vectors on this line, but it is present on this line.
and overall we call them a hyperplane.
No, overall, hyperplane is just this line. This
Okay.
hyperplane means any decision boundary. I am
Blue.
defining some points which should satisfy that these points should lie on hyperplane, so should satisfy some properties. So what properties, how they can be defined? For that, I am choosing any two vectors which are present on this line. So they can be arbitrary any vectors. Maybe the vector is present here, maybe the vector is present here. That's why I am taking x1 and x2. I am not defining whether they are close to the origin, farther from the origin. No,
Yes,
any
ma'am.
vector. Is that clear?
Yes, ma'am. Ma'am, hyperline, this line, ma'am, blue line, longest
Yes,
line.
yes,
Okay,
yes. Okay,
thank you.
okay. In this session, because there will be many mathematical terms, so I'll be asking you that whether it is clear or not. So maybe it's not possible for you to write or uh, open your mic and speak. So you can use just thumbs up so that I can have an idea that it's clear to you. Okay, so it will be easy for you as well. So now think about it. There are two ways I can represent what is written here. Okay, now let's say this x1 is on the line. It means the equation of line is more like beta transpose x plus beta naught is equal to 0. Is it fine? The equation of line should be like beta transpose x plus beta naught is equal to 0. Is it good? Yes or no? All right. So let's say I'm saying that x1 is present on this line. It means if x1 is present on this line, then x1 should satisfy this equation. So I can write beta transpose x1 plus beta naught is equal to 0. Similarly, I am saying x2 is also present on this line. So I can say beta transpose x2 plus beta naught is equal to 0. Equation 1 and equation 2. Is that true? It's a simple thing. I am saying that the equation of line is written like
Yes,
this,
ma'am.
and x1 and x2
Yes,
are
ma'am.
present on this line. So what can I say? That it should
Yes,
satisfy
ma'am.
x1 as well as x2. Now we can say that just take the just subtract both these equations. So what you will get? This equation. True or not? We just subtract both these equations, we will get this vector beta transpose x1 minus x2. Okay, so this is how we get this equation. It means that this equation is satisfying for any 2 points present on this line. Okay, now remember here, for this class we will be defining beta node always separately, and beta it means other vectors. So I am not converting x with the appending 1 in that. Okay, so I am separately modeling beta node bias as the separate term, and betas are the separate vectors. Okay, so that's why what I can say, that from this equation you can say, can you just can anyone tell me, if the dot product of two vectors is 0, then how the vectors are related to each other?
Ma'am, perpendicular.
True. So there is a property of orthogonality, or we can say perpendicular vectors. If two vectors are perpendicular to each other, then it means their dot product is 0. And the dot product is defined as, let's say I want to define the dot product of A dot B. I will write as A transpose B. Okay, so this A transpose B means dot product of A and B. Similarly, I can say this from this equation, the dot product of beta and x1 minus x2 is equal to 0. It means beta and this x1 minus x2 vector is also perpendicular to each other. Is that clear? Again, listen.
Ma'am, from the equation 1 and 2, we are equating both and obtaining the this equation, ma'am.
We just subtract the two equations. Just subtract it, then beta naught will be cancelled out, and beta transpose is getting common here, and x1 minus x2.
Yes, ma'am, got it.
Okay, so what I am saying, that from this equation we can say that first vector is beta, another vector is x1 minus x2. So it means that the dot product is equating to 0. It means that beta is perpendicular to x1 minus x2. Is that clear? Till now, any doubt? All right, thank you. Now, can anyone tell me what is this vector x1 minus x2? Anyone? Can anyone let me know what is this x1 minus x2? All right, look here. That's why I give you this geometrical representation. This x1 is a vector, this x2 is a vector. x1 minus x2 is this vector. Okay, if you are saying x1 minus x2, then it will be in the direction of x1, and it means the highest vector. If you will say x2 minus x1, then it will opposites direction, because vector has also magnitude and direction. Is that clear? So x1 minus x2 is the line actually. Is that clear? x1 and x2 are 2 points on the line, and this x1 minus x2 can be represented by this vector. So we can say that this beta and x1 minus x2 is equal to 0. The dot product is 0. It means that the beta is perpendicular to L. It's a simple thing. So how you can get those betas? The betas, first restriction is all the betas, it means this 2 and 1 will be perpendicular to this line. That's why in the initials, okay, the when I have not drawn anything here, the line is drawn, a normal vector is drawn here in which it is written as 2 and 1. Okay, yes, any doubt? Go ahead, Himanshu, do you have any doubt?
Yes, ma'am. Ma'am, as you were saying, ma'am, beta, the value of beta is 0. But it may be also the value of x1 minus x2 is 0. That is, both the line may be constant, except
saying the value of beta is 0, I'm saying that the dot product of beta and this line is 0. It means
Yes.
this beta is perpendicular to this line. So how you are getting these beta vectors will always be perpendicular to the hyperplane.
Ma'am, it is possible to beta maybe 0 or x1 minus x2 0.
Generally, it does not, it cannot happen. Just think about it. If beta is 0, it means there is no line.
No, run. Yes, ma'am. No,
So it doesn't matter. It doesn't, it's not a case which we will get. Ultimately, look, what is the main goal of your study is to get the hyperplane. Okay. Now,
yes, ma'am.
this to getting this hyperplane is very superficial term. In layman terms, in human language, we can say, okay, I want this hyperplane. But in mathematical term, what do you want? You want this equation, na? Because this equation is hyperplane for mathematics. Here also you know how many dimensions you are having. Here there are two dimensions, x and y, so you know there will be two beta value and one beta naught value that will define your hyperplane. So ultimately I want to model these variables. These modeling of variables we are doing from regression also. In regression, what we were doing, we are finding these beta. In the last class for linear classifiers, we are finding this beta using some MLE estimations, right?
Yes, ma'am.
Maximum likelihood. So here also we have to find this beta directly now. We don't have any discriminant analysis. We will directly model this. That's why, look, beta can be from anywhere, right? There can be from, we can have any line from this 2D space. So we are restricting our such space. We are saying we can find beta where the means it is should be perpendicular to this line. Otherwise, those betas will not be considered. So we are now restricting our space. What we do when we don't know anything, we have a good search space. What we do, we say that, okay, let's say I have to find out a particular type of tree in a forest, right? So what you will say, how it look like? So we just redefined our search by restricting some space. So here also we are defining some properties of hyperplane so that we can restrict our search space and we can converge more quickly. We can find the solution more quickly, right? So first property is this, the betas are always perpendicular to this hyperplane. Okay, now one question arises. You can have the betas because I told you in the starting we will define beta node and beta separately. What about beta node? So when you will get the value of beta, when you have some point x on this line, we can simply define beta naught because we know this equation. Okay, from this equation there are three things: x, beta and beta naught. If you know beta and x, you can easily get the value of beta naught. So that's how we can get the value of this beta naught. If x naught is another variable which is on this line also. Okay, so beta naught can be defined by beta transpose x naught. Is that clear? So in this way, we have defined the betas in the form of hyperplane in relation to this hyperplane. Is that clear? Yes, Himanshu.
Here, beta is a specific value in value which we have not known.
Yes, beta is 2 and 1 here in this hyperplane. You know this equation is written 2x plus y minus 3 is equal to
Yes,
0.
ma'am. Yes,
X
ma'am.
and y
Okay.
we know, but we don't know about 2, 1 and minus 3. The 2, 1 is beta and minus 3 is beta naught. Okay.
How you can take the transpose of any particular integer number? Here, you written
Trans
beta.
Look, transpose is like that.
Okay.
This is x and y. Okay,
Yes, ma'am.
so this is written like this. So its transpose, if I am going to take its transpose, it will be like x and y.
So,
Because
ma'am,
there are two variables, that's why we have to multiply. We have to multiply, like, let's say we have two values, 2 and 1, x and y. How will you multiply with matrices? So either you have to write it as
column, ma'am, row column must be
2,
equal. Then
1,
we.
and
Yes,
this is actually transpose. And actually this is the form of transpose. Generally we write vectors, look here.
ma'am. Okay. So here, ma'am, beta is representing a single equation, ma'am, according to you.
A beta is representing all the coefficients of your variables.
Okay.
Right, generally vectors we write in the column form, so we are writing 2 and 1 here as it is, but to get the actual dot product we take the transpose, we write it in the row and then
All
multiply
efficient.
by this, right? That's why it is written here, so it's more like this, right? Sorry, xy.
Okay, ma'am. Got it.
Xy, so you will be, it will be like 2x plus y. Okay. Okay, so we have defined properties of the hyperplane. Now just think about it. This beta node is a term, right? It will be some, like it can be of any natural number. So what we are going to do this, कि we are defining beta star. So beta star is normalized beta. It means when we normalize this vector in which the magnitude of vectors comes to 1, down to unit 1. Why we are doing this? So that we don't have the exploration of beta, right? We have worked with ridge regression or so. So for those purposes we apply normalization. So we apply normalization on beta node. All right, so how the vectors is normalized? Because vectors will have some components in it, right? Yes.
Ma'am, can you please repeat why again we are having normalization in here?
Generally, look, generally if you are not taking the normalized vectors, it means it can explode the terms for beta. It can have much value, it can have 100, it can have 1000, it can have lakhs. So we want to restrict our things for these variables, that's why we are taking normalization. So here also we are using, because we are using vectors, all right? So for that vectors we want the you can say the magnitude to be normalized as unit vector, or we wanted unit vectors, that's why wherever the unit vectors we are going to use, we will use this beta star. So ultimately we can say that we just all right, so wherever these betas are used, because these are vectors and when we are normalizing it, we are using this star. The same equation, this same thing, okay, is written in the form of like this. Because look, this fx is the same thing, okay, this thing is actually fx, and if we want to normalize something, we have to divide it by its magnitude. Correct? How we normalize a vector? If we have a vector v, we want to normalize it, so its normalization is vector v divided by its norm. Correct? So that's why we are also here, what we are doing, we are normalizing fx by dividing it with the norm of beta. All right, so this, look, this beta is having this equation, right? So if this is your fx actually, so what will be the f dash x? So if my fx is beta transpose x plus beta naught, so can you tell me what will be f dash x? What will be f dash x? Anyone? Beta. Okay, transpose we generally don't use it. Transpose it when we use the multiplication of two matrices. So it's more like that f dash x is simple beta. Okay, and here also we are using beta here, the norm of beta. So we can replace this norm of beta by f dash x. So if we are normalizing it, we can replace this equation either in this form or in this form. So these two forms gives you a conclusion or observation that fx is proportional to the signed distance from x to hyperplane. Now think about it. Just think here. Look. So this is your x minus x naught. Okay. Here, what I am going to write here, just look at here carefully. There is a vector x here. This is x. Okay, and some vector is here x naught. So what I am saying, x is outside the boundary and x naught is on the boundary. Okay, so what I am saying that this will be a vector and this will be a vector. Fine. Till now, is it clear? And x minus x naught will be the perpendicular on this distance, this one. So this distance can be seen as the length, the distance of x from this line. Again, listen, there is a point x which is outside the boundary. There is a point x naught which is on the boundary. So we have these two vectors. So x minus x naught geometrically gives you a vector or the distance from x to this hyperplane. So that's why this x minus x naught is giving you the vector which nearly equals, which gives you the distance of this point to the hyperplane. That's why we are saying this fx is proportional to the signed distance from x to the hyperplane. Signed means it can be positive, it can be negative. Okay, and if we are normalizing it, so normalizing beta to unit norm makes fx directly equal to the exact sign distance, because if we are normalizing this vector, it means you don't need this. All right, so it means it is directly giving you the exact sign distance, or we can say it is proportional to the sign distance. So basically what we can say that for any point x in this whole graph, your fx is beta transpose x plus beta naught will give you the distance, the proportional distance from the hyperplane, whatever the equation of hyperplane is. So if let's say the point is on the hyperplane, then obviously it will be equal to 0. So the distance will equal to 0. And if it is, let's say it is equal to 6, then it means there is the distance between the point and the hyperplane is 6. And if it is minus 6, that's why it is written it here as sign distance. So you can have plus value or minus value. So let's say your plus value is in this direction and minus value is in this direction. So using the sign values, you can classify the points as plus class or minus class. Is that clear? So let me reform all this again. So what I am saying is, till now we are saying there is a line, I'm talking about 2D here so that you can easily visualize. There is a line which has some equation like beta 1x plus beta 2x plus beta naught is equal to 0. And first property is the betas are always perpendicular to this line. Secondly, this line will give you some value, all right, because this, let's say this line is equal to 0, it means this is your hyperplane. But let's say this line gives you the value 6, this line gives you the value 11, this line gives you a value d. That d means which point you are using here, is it giving you the proportional distance from that point to the line or the hyperplane. If it is positive, then it is one side of the line. If it is negative, it is another side of the line. So is that clear? This is the geometrical and mathematical view that how you can formulate your problem mathematically and geometrically.
Yes.
Okay. Is there any confusion? I think it has. Is that clear or not? If you have any doubt, then go ahead, because we are using all this again. Is that clear? Yes or no? So what I am saying is, let's say I am creating this hyperplane. So this hyperplane will have equation equal to 0. It means all the points on this, right, will equal to 0. 0 means 0 distance. So it means it is on the line. If let's say some point is here, okay, some point is here, some point is here. So if I put this point on this line, then it will not obviously gives you 0. It will either gives you some value plus d or minus d. So if it is plus d, it is this side of the line. If it is minus d, it is this side of the line. So this d means the distance of this point to this line. So that's what I am saying. So, and how you get this from this equation, because fx is directly proportional to the distance. So I'm saying the value of this function will gives you the distance proportionate distance, let us say, so we can easily relatively use it. So this distance is the value of fx. Okay, so next thing is this example. So this example is a very simple example which gives you an idea that how to calculate these values. So let's say your hyperplane is giving like this. Okay, so 2x plus 3y minus 3 is equal to 0, where beta 1 is this, beta 2 is this, and beta naught is this. All right, and your point is 2 1. So it means, let's say this is the line and this is the point, somewhere all over the 2D plane. So now what you wanted, that you wanted to compute the distance. So as I already told you that the distance can be computed with the help of this fx. So just put this point on this equation. So how you can put this? 2 into x is 2, y is 1. Just put 2 and 1 here and you will get some value, right? So what I have done here, I calculated this fx. So because x minus x here is p, that's why I'm calculating here fp. So what I'm doing, 2 into 4, oh sorry, I have, the point is not 4. Okay,
And
It should be
I know.
2 and 1, right?
actually let's say the point is 4 and 2. 4 and
Yes.
2. Okay, let's change the point. Okay, by mistake I have written. So point is 4 and 2. So 2 into 4 plus 3 into 2 minus 3, it will give you 11. What I told you, this is the proportionate distance, not actual. So if you get the actual distance, you have to divide it by beta norm. So how you calculate beta norm? You know the beta, 2 and 3. Oh, here also, actually I have merged two questions together. So here it is actually 3. Sorry, I will change the slides and then upload. Okay, so it is 3 and it will be now here 4 plus 9, so it is more like 13. Okay, get it? Is that clear? So now you have this 11 and this 13. So you will compute the distance as 11 by under root 13. So this will be your exact distance, and if you are not using this under root 13, then it will be your proportionate distance. Is that clear? It's a simple thing. You have a hyperplane, you have a point, you want to calculate the distance from the hyperplane, just put it in the equation, get the value and divide it by the beta norm. This is the exact value. Is that clear? Anyone having any doubt in this? All right. So
No,
now
ma'am.
you, yes. Any doubt?
Clear? Clear.
Any doubt? Okay.
Ma'am, applying this process, we can deterministically say that the candidate point is falling over the class 1 or class 2, the either side of the line, right?
Yes, yes, yes.
Okay.
We have
That is the ultimate objective.
yes. This is the first thing that we have started with. That you
Right.
have a line, and if that value is greater than 0, then it will belong to one class. If it is less than
Yes,
0,
yes, yes.
then it will belong to
That is
another
the
class.
basic premise, right?
Yes, yes.
But ma'am, if we actually do not have the equation itself, so is there will you teach us the how to obtain the
Yes,
equation like 2x minus plus
yes.
3y minus 3 0? Uh,
Actually, what you are saying is the ultimate objective, right?
yes, ma'am. Yes,
Right.
yes, right,
So
right.
now we are just processing each term step by step.
Step by step, right?
Right,
Okay,
right. Now we will
okay,
see
sure.
how to get this 2 and 3 or minus 3, right?
Yes, yes.
Yes. So
Ultimate
there,
object. Yeah.
yes,
Mm.
there will be two algorithms we will be discussing. First is your perceptron,
Okay,
and
ma'am.
then
You just carry on your own pace. No problem.
okay,
Yeah.
okay, okay. So first algorithm is, as I told you, about perceptron. So perceptron, why it is very important? Because it leads to a very important study that is called neural networks or deep learning, which I think this is will be the topic of week 5. We will discuss it there also. So perceptron decision is, we have started like we want to model, as sir also said, this how to get this betas, right? Ultimate objective. So perceptron say, don't think much about it. What we can do is, let's go with the base layman study. We can start with classifying the data. We just start with one hyperplane, and if I get misclassification, I'll arrange it. Look, We want to find it out. As the previously I told you, there is a big search space and I want to restrict it. So for the restriction, I told the betas are always perpendicular to the actual hyperplane. Okay, this is good. But how to proceed? How to go? So Perceptron say, let's not think about anything. Let's start with the first given example. We just simply draw a line, simply draw a hyperplane. If it is good classified correctly, then good. If it is does not classify correctly, then we have to think about it. Okay, so it's a very layman approach. If we are
Kind
finding
of probing method, ma'am, right?
yes, you can say like that.
Okay,
Because,
okay.
okay, so how to define this? So ultimately, this is the simple thing which we have started with. The fx is greater than 0 class positive one, otherwise negative. Okay, positive and negative means these are two classes. Why we have defined this positive negative? So that it is easy to see. Okay, greater than 0 related thing. So ultimately, it means this y is plus 1 and here the y is minus 1. Okay, so this y you will define obviously, right, according to the class. So now the second point is when the point will be misclassified. How can you say the point is not classified? Because I wanted class 1, so it should be greater than 0, but it is not giving you greater than 0. That's why it is misclassified. That's why the opposite things are written here. Don't get confused here. If your function is negative, right, it should give negative answer, right? But the actual class was positive. That's why it is called misclassified. So these are the misclassified definitions, the opposite of the correctly classified, as you can see here. So I want to say that don't get confused here in the two definitions. Yes, go on, Himanshu.
Ma'am, here, what is the meaning of misclassified? Only for fx negative and fx greater than 0.
Okay.
That's why you call
Okay,
misclassified.
okay. Let's say you have defined some boundary, okay? This is your boundary, and I am saying if it is greater than 0, then it should be plus 1. If it is less than 0, it should be minus 1, correct? Let's say there is a point. So this plus 1 class is defined by this squares, and minus 1 class is defined by this crosses. Let's say there is a there is a square here from this boundary. For this boundary, the square is here. So it means according to this boundary, what you have drawn, what will be the value of this from this hyperplane? It should be negative or positive. Let me know.
Negative, ma'am.
Negative, but it should be positive, right? You are getting wrong answer, but it should be like the hyperplane should give you positive, correct? I'm saying should give you, and what is giving is a different thing, right? You said according to this hyperplane I'll get negative. That's what I'm writing here. If you are getting negative but the actual class was positive, it means you are wrong. So misclassified means wrong. So while drawing this hyperplane, how many uh, um points are not correct? Okay, so let's say for this hyperplane, can you say that this point is correct? Yes or no? If I draw this hyperplane for these two classes, this plus 1 and minus 1, will this point be correctly classified? Yes or no? Hello? Hello?
Ma'am, is it the square you are mentioning?
Sorry?
Is it the square you have drawn?
Yes,
Just
yes,
been.
yes. Just think
Yes,
about it.
if it is misclassified, that means the line itself is not in its actual place. It's not the ideal line to be drawn. Line
Same
should be
here.
modified.
Yes, that's what I wanted. These are the
Yeah.
two classes, okay, red and blue. And let's say this is a your plane, okay, and there is one class here, let's say here. So what I wanted that this is this. So what I wanted to shift this line, black line, towards somehow here. Yes or no? It should be somehow here so that I can get all the points to be correctly classified, right? So misclassification is for this point if the line black one is used. So that's why I wanted to know how many points are misclassified. So for those misclassified points, if they are from class +1, then your function is giving you opposite values. If it is -1, then it is giving you plus values. So that's why it is written the opposite what is written here. Okay, so these are the two different things. Yes.
Ma'am, will the question specify whether it is misclassified or not?
Actually, you can get it out. You know, this perceptron learning is supervised study. So you know the ground truth, and after getting from the function, you know the value. So if you are not correctly classified, you will know it. However, because of this value, let's say you are getting from the function the negative value and your class is positive, then you can say obviously this point is not correctly classified from my function. So why I'm
If it's
defining this?
correctly classified?
If it is correctly
If
classified,
it's Yes, ma'am.
yes,
If it is correctly classified, then it is the
then
above
good, then
point,
good,
ma'am. Like,
then you are good to go, then the problem is solved. Why I'm defining this misclassified? Because the perceptrons say if the line you have and the points are there, if it is correctly classified, then the line is good. But if there is misclassified, then I have to adjust the line. Okay, look, when you are training something, let's say I give you some data. Okay, you are wherever you are sitting, let's talk about 2D. There are some objects there that are scattered, some blue objects, some red objects. Okay, and what I told you ki you have to separate those objects, you have to make a boundary. Condition is you can see one object at a time, you can't see whole data at once. You have to move one by one because it's a stepwise procedure. So what you will do, you will take first object. Okay, so you will take first object, you say okay, it's let's say the objects are of blue and red color. So let's say you have got the blue object, then you randomly draw a line simply because you don't know other objects where are they. So you just randomly draw a line. Now you get another blue object, you will try to fix that line. Okay, then you get first red object, let's say. So for that red object you will fix the line. Okay, the line should be in between these two red and blue, right? Now you get more and more, as you get more and more red and blue objects, you will fix that line. Yes or no? Are you getting the human approach how you will start with?
yes, ma'am.
Right? So what you will first think about, it's a very it's a very simple procedure, so we do the steps very quickly. Just modularize all steps. Just think about you are having the line at step at which you are having. Okay, you are having that line, you have drawn that line. Now I give you the another object which is of blue color, and you see okay, this line which I have drawn is not satisfying for my blue point which I have just got it. So what I will do, I'll just adjust the line. So as you get the new object, if that object does not place where it should be, then you adjust the line. If it is placed, then you say the line is good, no problem with it. So this is how we are approaching the perceptron decision also. So we are saying because the class is +1 and -1 and the values are also positive and negative, so we are going to use some signed the sign thing. Okay, if we are getting the positive value, it should be positive, and it is, if it is negative, so we will shift the line towards it. Okay, so as we are getting the more misclassified point, we are shifting our line towards that. So it's more like going here and there. So that's why it's a very complicated thing. If the data is more complex, you can't just fix the line on the basis as one by one the objects are there. Okay, yes,
And
go
so
ahead.
basically, after finding the function and also the class, we are judging whether it's misclassified or not.
Yes, you can say. So we will be solving one example for this. Okay, so ultimately
Yes, ma'am.
what is our objective is that we want to minimize the distance of misclassified points, right? So let's say we have a line, and obviously you will not get the accurate line, sometimes you will have noise also, right? So we want to minimize the distance of misclassified points. So, or in other sense you can say we want to minimize the misclassified points. So for this minimization, just think, look at here. So just think about it. The actual thing. If the function value is positive, class is +1. Okay. So let's say function value is positive. Function value is positive. class is +1. Function value is negative, class is negative. If I just multiply these two things, whether which value I get? Here, will I get positive or negative? Function value is positive and your actual class is also positive. Okay, so by multiplying these two things, what I will get? A positive value or negative?
Positive.
Positive, ma'am.
Positive.
And if the function value is negative, the actual class is also negative. This is still true case. So if I multiply these two things, what I will get?
Positive.
Positive.
So it means if your points are correctly classified, then the product of predicted value and the true value is always positive. Can we deduct it?
That is, ma'am, true positive actually.
You can say it true positive, but I am saying you because we are going to use this sign process, this sign positive or negative for our studies. That's why. So it means that if the product of y and fx is positive, it means you are good, you are correctly classifying. But what say, I am taking it into the another now aspect. If your function value is negative, okay, function value is here and y value is here. So function value तो आ रही है आपकी negative, but वो थी positive. So the product will be
Negative, ma'am.
राइट अगर फंक्शन वैल्यू आपकी पॉजिटिव है एंड y वैल्यू आपकी नेगेटिव थी, इट मीन्स दीज आर नॉट करेक्टली क्लासिफाइड, आई विल गेट नेगेटिव वैल्यू. इट मीन्स व्हाट आई वांट टू डिडक्ट हियर, this the product of y and fx gives you a distinction of correctly classified or not correctly classified, because you were saying na ki how to get this misclassified points. As a human perspective, it's easy to say ki, okay, this is misclassified, this is not, this is correctly classified. But in mathematics form, we need proper function, we need proper objective. So now I can deduct that if I multiply this y to fx is beta transpose x plus beta naught. Okay, if I just multiply this and if I am getting positive value, then I am good. But I want to reduce this negative value. मुझे negative value को reduce करना है. Okay, one thing, just I am giving you some examples. Okay, if it is positive, it means I have to maximize the positive and minimize the negative, right? So let's say which value is more minimized, let me know. -5 and -4. So what is the minimization rule say? Which is the minimum value here?
-5.
-5. So the value -5 is minimum, right? So, but just think about it. This negative is just for your sign. It is not giving you actual -5. Just think about this. Just
Table.
hello, any doubt?
No, ma'am.
So what I am going to say is कि if this value and this value is actually are just, these are actual negative values, but here this sign means the positive class or negative class only. So that's why in our objective function we put a minus at the end to minimize it. Because here also I want to say that in -4 and minus, here I want to minimize, right? So I want to minimize, I want to get -4 irrespective of 5. This minus sign is just giving you an indication that your points are misclassified. That's it, irrespective. That's why we are putting it here minus extra minus. So what I am doing here, for each misclassified point, here the summation is only for misclassified points. If the points are correctly classified, we will not use it. Okay, so we are using the objective function as y I fxi. So now this objective function, and you just take a summation overall for all misclassified points, it means all the negative points you are taking, no positive points are taken here, and after that a final minus value is taken. Why this minus is given here? Because if I wanted -5 and -4, the minimum value is -5, but it is increasing the magnitude, right? So this negative sign is only for indication of class, not actual minus, that's why I am putting extra minus sign. And because I am putting extra minus sign, there is another reason, because I am just adding all the points for misclassification. I am not adding the points for good classifiers. Is that clear? Is it clear?
Ma'am, repeat please once again.
Okay, so what I wanted, now you get this objective function which you want to minimize is yi fxi, which I told you from this one and this one. Either you want to maximize these positive points or you want to minimize these negative points. Okay, this is one thing. Now I am saying the minimization is much more easier to solve. That's why I am going towards minimization. So minimization ke liye I just add all the value of this function for misclassified points. So for all misclassified, these values will all be minus. So minus of minus of minus, you will add all the values in magnitude, but you will get a minus sign. Let's say there are 3 misclassified points with value minus 5, minus 4 and minus 10. So what you will get, 10 plus 4 plus 5, that is minus 19, correct? Is it true?
Right.
Right. So it means this negative is just used for indication that you are not correctly classified. The magnitude is just adding it up, right? So I want to reduce this. I want to remove this. That's why I am putting a single minus sign here. Because here I am not adding any positive value. These are all negative values. That's why it is written here for all misclassified points. Okay?
Okay. Okay.
All right. So basically our goal is to just minimize this. So you know how minimization work. The minimization work basically with derivation rule. So go start the, I'll talk about this later. So your value was like yi beta transpose x plus beta naught. Okay, this was your function. This is your summation, this is negation is there. All right, so if you derivate this d with respect to beta, what you will get? yi xi, because beta naught will not be used. This is the partial derivative. If you will take the derivative with respect to beta naught, you will get only yi. This is very simple. Just use the derivative. So derivative yi beta naught xi plus yi beta naught. Just open it and take the derivative. Is that clear? Is that clear? Yes or no? Just give me some emoji. Okay, good to go. So basically what we do is, when we have this type of function and we want to minimize it, there is a process to optimize it in step by step.
Ma'am,
Yes,
ma'am, can you please show the previous slide?
this one.
Ma'am, before that. Ma'am, so basically, for misclassified, will always result in a negative value. So that's why we are including a negative in the equation, ma'am.
The result is not negative. The product of y and fxi will be negative.
Yes, ma'am, that's what I mean. So therefore, to make it classified, we are adding negative in the equation, ma'am.
Yes, because we want to minimize the value, right? We want to minimize misclassification. So the less the value of this negative thing is, the more we are getting a good hyperplane.
Yes, ma'am, got it, ma'am. Thank you.
Okay, so basically how we approach this gradient descent. So I'll let you know about gradient descent. Basically what it does is,
Ma'am, one thing I've seen that those negative values are actually forming the false positives and the true negatives. In fact, it is an observation, just an observation.
yes,
Actually,
you can say that.
yeah, right.
So basically what gradient descent is, previously what we have learned, if you want to find the minima, right? We want to find, the equation is that you want to minimize this distance, you want to find beta and beta naught such that this distance is minimized. So actual problem can be solved with the help of derivatives. That take the derivative with respect to beta, put it to 0 and calculate the value. Then take the derivative with respect to beta naught, put it to 0 and calculate the value. But as you can see that here there are no betas, here there are no betas. So how you will solve the betas? So for that, because this problem is maybe like not a good problem to solve directly from the derivative, we use a stepwise procedure, which is like Newton-Raphson we have discussed in the last class. And here the approach is called stochastic gradient descent, or we can say gradient descent. So what gradient descent is doing, let's say this is your function, okay, this is your function, and we want to find the minima. Minima means this point, all right, and we are here somewhere here, right? So we want to minimize this d is like a function, the minimum value is stuck here, and we are starting from this position. So we want to jump from here to there, point A to point P. Okay, this is our main point. So basically how we jump here, we don't know actually. So it's more like a hill climbing approach. So what we are going to do, we just start with some gradient information. Gradient information say that it will lead towards minima, but with some small steps. So it will give you the direction, because this function is not very good, right? It's a very complex function, so it will change its direction at each step. So it will give you small direction. So what we are going to do, the betas at level A will move to the direction, this direction. Now the betas at point this will move to this direction. So similarly, when you are moving toward this direction, you will lead some convergence. So from here, if it is giving you, it will be around like this here. So you will get some idea after many steps that your minima point is lying here. So what you are going to do, we start with some initial value of betas. Okay, we randomly, like I said to you that if you are the room example, you start with random hyperplane. So you start with random values of beta, you get some information ki, okay, let's move in this direction. So you slowly starting moving towards that direction. So it is also recommended that we should not we should not take large jumps. Okay, so it's not like that we are jumping from here then here. No, we are jumping from maybe here. So these jumps are dependent on a factor that is called learning rate. So it is generally represented by neta. So it is, the value of this is more like 10 to the power -3 or -4 or -5. It means it's so much small. Okay, so as you can get it, if the value is very small, then the steps will be more. It will take time to reach to this minima point. If the step will be large, maybe you will skip the minima point, you will not get it. So we have to adjust it somehow. So we will take one example, one question, a simple question, and here I am not using the summation part. Okay, so I'm because I wanted to give you some steps, that's why I'm not going towards this summation part. Otherwise I'll let you know how you can approach with that summation of misclassified points also. So I'm taking one point at a time, as I have given you an example of room. So these parameters, this learning rate we will be defining before experimenting. So what we need is, first, this is your data, simple data. It has 4 points, this 1 2 3 4, and these are your classes, +1 and -1. Now the first step is initialization, because I'm saying I want to know the beta and beta naught, and you start with this some initial vectors. If you don't know, start with 0, it's more recommended, or you can start with some random vector.
Ma'am,
So
by take a beta equal to 0, 0.
क्या चीज
Ma'am, by default, we take initial weight vector beta equal
means it's more like a magic number 0. We don't know any information, let's start with 0. It's more like
to.
that. Okay, because we can't choose much larger values for beta also, right? So this is your at iteration 1. At iteration 0, we are choosing 0 0, just like that.
Oh,
Okay, it will not give you any plane somehow, but it will start with your processing steps. It's very true.
so ma'am, it is taken by itself, ma'am.
Yes, I am taking it by itself. Otherwise, you can start with 0.5, 0.5. It will give you maybe more good plane. It's more like 0.5, 0.5. At least it will give you some plane. Na? 0, 0 will not give you anything. Okay. And for computation purpose here to solve, I am choosing lambda neta 1. Otherwise, its value should be 10 to the power 4 or -5 or -2. Okay. So for showing you some calculation, I am choosing it 1 here only. So first step, First step is I have beta value, beta naught value and eta value. Okay, so I will start with this point. So what I will do, x1 is given, x2 is given, y is given. Okay, what I want to calculate is, first I will calculate f of x. So f of x is calculated with this beta value. So 2 into 0 plus 1 into 0 plus 1, you will get 0. Okay, so 0, it means it is on the line, so it is obviously not correct because it should be classified to plus 1 or minus 1. So I can define it as incorrect. Good to go.
May I repeat once, sir?
I want to find whether the value is correct or not. So you have to go with this yi, this yifxi, right? This is what we have proven just now, that if this value is negative, then it is incorrect. If it is value is positive, then it is correct. Okay, right? Fxi is beta x1 plus beta x2 plus beta naught. This is your fxi. So just put the value 2 into 0. Here it is 2 into 0 plus 1 into 0 and plus 0, this beta naught. So plus 0, it will give you 0. Okay, 0 into 1 is 0. So it is incorrect, right? Correct. Incorrect ke liye what we have to do, we have to calculate new beta, obviously. So for new beta, we know to find the new beta, it is the formula. This formula is used. So it means in gradient descent, whenever you want to find the new values, so new is equal to old plus neta and the derivative. This is the general rule. So if you want to find new beta, then derivative with respect to beta. If you want to find new beta naught, then derivative with respect to beta naught. Is that clear? So that's why I have written here beta new is equal to beta old plus neta. This is your d by d, and this is your d by beta naught. This we have already calculated in this slide.
And how to find beta old, ma'am?
Beta old is, we have started with this. This is your beta old now. Right? We
Okay, ma'am.
started with some beta and we want to change it now. So we just put in this equation and we will get new beta. Simple. So how you are going to get this new beta? Just look at it here. Old beta is 0 0. Okay? Neta is 1 and yixi is means your this 0 into yi, that is yi is, for this the yi is plus 1, so it is written as 1, and xi is this 2 1, so it is written as 2 1. Just calculate, simple calculation.
Ma'am, can you once again explain why 0 is incorrect?
Okay, 0 means if this hyperplane is here, it means the 0 point, it means let's say this is your a point. Okay, this a point will be lying somehow here. Is it true? If it is falling on hyperplane, then its value is 0. You know it.
Yes, ma'am.
So it is not, it cannot be classified as plus 1. It should not. It should have some value, whether it is a small value here, but it should be plus 1. It should have some magnitude more than this 0. Okay?
Yes,
So
ma'am.
that's why it is incorrect to me. Alright? And if it is incorrect, I'll calculate beta nu. So now this is now beta is changed to this. 2 1 is my new beta and 1 is my new beta naught. So what I will do is I will again calculate for point B. I will use 2 and 1. So 1 into 2 plus minus 1 into 1 plus 1, and it gives you 2. Now you will say, ma'am, how this is incorrect, this is positive, because here while making this slide, I am just using the function value. I am not multiplying it yy. So if you will multiply it with yi, the signs are opposite and it means it is incorrect. It should give you minus value, but it is not giving you minus value. Okay? Is that clear?
Ma'am, so y is -1 and we didn't get as in minus symbol, so it's incorrect, ma'am.
Yes, yes, you got that. Okay, so
Yes, ma'am.
okay, the product is negative, you can say. For computation, for to make the computer know it, either you will say the both the signs will be opposite or the product of the sign will be negative, you can say. So it means it is incorrect. Again, calculate new beta. So here again, old beta is 2, 1, neta is your 1, your y is -1, x is 1 -1, and just calculate new beta. Similarly, calculate new beta node. Now, this is our next new set of betas. For C point, if you will say, I get -5, similar calculation, so it means it is correct. It is correct, so I will not update anything. So, can you see here, if I am getting the correct answer, I will not update my hyperplane. But if I am getting incorrect answer, I will again update it. Is that true? Is that clear? It's a very simple approach.
Ma'am, one
Hmm.
point that once we get the incorrect value, then we are getting the anyway we are getting the new value of beta new is obtained.
Yes.
But can we try the previous value like x1 in the set of x1 and x2, uh, two one of the initial I mean the first value, first element.
Okay.
So we
Your
could try with the new I mean the new beta with the old values of the x1 and x2. Is it possible that way?
it means you are saying as we are moving to, down the data, we are changing
Yes.
betas, but we are not evaluating on previous x values.
Right, right,
Right.
right.
So that's why I'm not saying it is converged. I'm not saying it's the
Okay.
first step. That's why it is written here iteration 1. Iteration
Oh,
1,
I see.
when full data is completely processed by this whole betas. Okay.
Okay, okay,
Now,
okay,
next iteration, you will have new set of betas, go for the next iteration. Same process. Here,
okay, okay,
maybe
ma'am.
the value will be updated or not. Okay.
Yes, yes, yes.
Right.
Got-
So these many iterations will go on, and why I have chosen to update each and every point so that I can give you an idea of these iterations. You can have more variation in these iterations. Okay. So look at the final. Uh, okay. So basically, at the last, I get this type of iteration. Okay. So it's more like the betas are there. You can plot it and get the answer. And you can say that after that, this 0, why I am writing it here, correct here, because at the last time, the betas are updated here. And when you update the beta, you are moving towards it. So the moving towards that incorrect point, it means taking that point on the line. And if you means you can start.
Distance minimization. Yeah.
Yes, you can say. So basically it will not update afterwards. Another thing in the formula,
Madam,
when
are you getting the new hyperplane, madam?
yes, actually I should have um, plotted here. Maybe I just forget it where I have plotted. So if possible, I'll plot the hyperplane. It means, let's say this is your hyperplane. Okay, this is your first hyperplane. This 2, 1 and 1. Next hyperplane is 1, 2 and 0. Next hyperplane is 3, 0 and 1. Next hyperplane is 2, 1 and 0. So this is how the hyperplanes are changing. So the direction of the line may be moving towards to and fro, right? If you will plot it, you will get it.
Yes.
Second thing, in the question, means in the equation that we have used in the distance, we have used this summation sign. Okay. Another approach is this iterations which I have shown you is on one data point at one time. Another approach can be this same data is used for all points, and for the incorrect point, I take the summation. Then I change the beta. So it's more like whether you wanted the correction to be done at single point or the average of it. That's what is this summation means. So these are the different approaches of gradient descent when you want to update your betas at one point at a time, or the summation or the average of all points. Okay, so this is how let's say these are the 3 points, and then we want to somehow use that That's a separate case. So I want to give you just a glimpse that what this summation means here. Okay. So this is all about perceptron. Basically, the major problem is this issue with non-linearly separable data. So if your
Ma'am,
data is
one point, ma'am. Why can you repeat the why the last zero was not incorrect? I just missed out.
basically this last zero, no, this one. So in the previous
Yeah.
step, there is no update. Here the point is updated, then no update and no update. Okay. So because for this hyperplane updation, these are updated, all three.
Okay.
Okay.
Okay. Okay.
And only this is to be checked. So I just checked it here. It is also correct. Maybe when you go with this and again recompute the betas, you get the new hyperplane and what you said actually just now, the minimization. It is on the line, but it is minimized for all other points also. So
Okay.
it may or
Okay.
may
Okay.
not be converged again. So
Yes.
that's why
Yes.
for computation purpose, I have
Following the tendency or the yeah, right. Okay.
Okay, so major problem is with non-linear separable data. If maybe your just separating boundary is not a single linear separable, but it is non-linear. So it means, let's say your data is more like this. Some points are inside this circle and other points are outside this circle. So how to classify? You need this circle. So this circle is not linear at all. So for that we can't use this perceptron. It will not converge firstly. Secondly, it means gradient descent is not good approach for this. Okay, so for here we can't use this simple approach. So for these perspectives we will be using some other types of algorithms and
Ma'am, in those cases, is there any boundary of the second class? I mean, it seems like open.
it is open, but it's not linear at least.
Yes. Yes. Okay.
Ma'am,
Yes.
ma'am, can you explain the previous slide at last of the classes, ma'am? Yes, on this slide, any one of them,
Okay.
step one.
Let
In
you can you get this these all steps 3 4? Do you get how we are getting it through?
yes, ma'am. Yes,
Okay.
ma'am. I am confusing
Here
you how it is correct, incorrect.
uh, right. So you are updating your betas. For every incorrect value, you are updating the new beta. Okay. Is that good?
Yes, ma'am.
Okay. So let's say at this step, your betas are updated, and this is your updated beta. I started with this A point. It is correctly classified, so no update. At this B point, I update the beta. So now my final beta is this. Using this beta, I take C and D, and it is also not updated. Okay. So here I have updated it. For this is good, this is good. This is left to check. Okay. So I'll check it again for this beta. So it is also good to go. So here till now no update, all the points are no updated. We just go on this procedure. So I can't go with more slides or more iterations because it is giving 0. It is nearly correct to me. You can start updating it also, making it incorrect, and see what happens for more iterations. But 0 other data is actually giving me the good option that after this the betas are the optimal betas are this. Getting? Using this beta value. Okay. All right. So next we'll go it means what we are doing right now, we are just modeling a hyperplane in between the classes. So we have considered linearly separable data. Present also we will be considering linearly separable data. But do you think it's a good approach? It means it is what it is just doing. If you have some points here, if you have some points here, and you are just defining a boundary. Okay, your boundary is like this boundary can be like here also. So there will be infinite number of boundaries which just consider the misclassification. Okay, so how can you say that which boundary is more optimal? So do you have any criteria of optimality? Do you think what can be the optimal criteria for choosing one of these hyperplanes? So can any one of you tell me just by an intuition that which boundary you will choose, that okay, this should be the optimal one? Anyone?
Repeat your question once again.
I am saying these are two classes, red and blue, and I draw three hyperplane. So can you say these three hyperplanes can be the result from your perceptron algorithm? Any three can be, because all three is giving you correct classification. And your objective of perceptron is we should not get misclassified data. True?
Ma'am, try to find the distance, distance between the points, which.
Yes.
We need to maximize the distance.
Question, ma'am.
Yes. So just by the intuition, what is saying that the hyperplane which is maximizing the distance of both the classes of each direction, right? In the positive, in the negative. Now question arises, maybe we can have a hyperplane. It is maximizing the direction in this red classes, but it is not very accurate for blue classes. So another criteria is also that it should be in between. Okay, and how you will get this maximum direction? It means I want to define something else here. So first thing, closest point. So it means, let's say these from these you this one red classes, this is the closest point, this one, okay, this one, and from the blue this is the closest point. So I want a hyperplane in between these two closest points, first thing, which will maximize the distance between the hyperplane and these closest points. Secondly, this hyperplane should be equal distance to this blue plane as well as from red plane. It means it should be in between. Exactly, I want a hyperplane in between these 2 points. Is that clear? So two things, maximize the distance. Second thing, equal distance. Is it true? Is it good? All right. So using
Yeah.
this, we will formulate it. Yes, any doubt? All right. So now we will formulate this question. So concept of margin, you can say that, look, there are two pictures are here. The margin is small, here the margin is more, right? So it means these are called as max margin classifiers. So it means we want to
Can you please
maximize.
show the previous slide once more, ma'am? Ma'am, what does the last two point mean, ma'am? Like,
This one?
at,
This one?
yes, ma'am.
Okay, let's see from this. So let us say from in this figure, I draw a hyperplane like this. Okay, so you are saying you want to maximum margin from both the closest point of classes. So it is maximally marginalized, but it is not in the between. So from those also I will select which is exactly at equidistance from class A and from class B. So that's why it is written equal distance from hyperplane for a closest point on both sides. So hyperplane, equal distance, both side, class A, class B.
Ma'am, but this we will find by using mathematical equation, ma'am.
Yes, mathematical equation. So we are just defining
And
our
then what is the
Ma'am,
then
can
what's the
we derive
difference
it?
that they asked for maximizing the distance of the closest point, ma'am? Here they are telling
maximizing the
equal
distance.
distance.
Maximizing the distance means, that's what I am saying. Let's say this is the point and this is the point, and if I define this one, so maximize means this distance plus this distance and average. So you can have this maximum value in when you will get this, but this is not equal. It can have, let's say
That
it
is
is
not the shortest distance, na, ma'am. It is the, I mean, the orthogonal distance, right? I mean, the perpendicular distance from
no,
the.
what I am saying is, let's say if it is in between, okay, and its distance is d, its distance is d, so the average distance will be d. All right, let's say
So
I
can we
have.
say that, ma'am? 1 minute, ma'am. Can we say that they are telling us to either have equal distance for the closest points or to maximize the closest point, ma'am?
We want to maximize the distance also and the distance from both the classes should be equal. It means the hyperplane should be in between. That's what I want also. Maximize is not a number, you know. You can get 4 or 5. Either you get 4 or 5, it doesn't matter. It's a very small difference.
But ma'am, there is a question that ideally the sample point may not fall in equal distance from the hyperplane. Is
No,
it as a sample situation?
yes, you can say that, but we are putting some constraints. So when you are putting the constraints, you apply all the knowledge what you wanted. You wanted to have all things which you want from the system, that I want a hyperplane just in between. So just in between means it should be equidistance from all the closest point. Another thing you can say that this will be helpful when you are dealing with some soft classifiers. Let's say this is the data, okay, this data, and this the other class is shown like this, okay. Maybe if you want, when you want to maximize the distance, it can happen that some of the misclassification can occur. So your classifier can be like this, maybe means this distance is and choosing this closest point is more appropriate than choosing this closest point. It may be wrong. Let's say I'll give you an example. We will have some example in soft classification, then I'll making it more clear to you. It means we wanted two things. First, that we want to maximize the distance of all points. Actually, it's more than it's written as closest point, but it's more like I want to maximize the distance of all points here and from all points here with this hyperplane, okay. Secondly, I wanted it is in between this closest point. You can treat it like this. Because when you are the data is given to you, it is not the whole data in the world, it is just a sample of the data, right? So maybe you can have some points which are near closest to it, but the major points are lying far behind it, okay. So we wanted to maximize the distance between these two classes. Actually, ultimate goal is, so the hyperplane, it should be in just in between the classes. Clear?
And that is to be exactly in between, right?
That is, yes, we wanted exactly in between, but we'll formulate it actually, okay.
Okay.
So let's go with the mathematical formulation here. So ultimately, you know this formula, that this is the distance, this is your fx, this is the distance of any point for the from the hyperplane. So what they wanted, that this distance is to be greater than m. So this m is a very large number. I want to maximize m such that the distance of every point to the hyperplane is greater than 1, greater than m. So this m is to be maximized, means I want a hyperplane which will maximize this distance m. So if there are some points here, if there are some points here, and I wanted a hyperplane, so I want to maximize these distances for each point. So some points will be closest, some point will be farthest. So I wanted this distance to be maximized. All right, so it's a simple optimization problem, but we don't know about m, how much this is to be there. Okay, this yi fxi is the same function that we have used in your perceptron. Here I am not using as a negative sign because it is for all points. I'm not specifically saying that whether it is for misclassified or classified, I'm not telling anything about right now. So I'm just creating an objective function yi fxi should be greater than my, because this shows the distance, and this distance should be greater than some value m, and we want to maximize this m. Now with constraint, we have to follow some constraint, because the beta norm we wanted it as 1, right? Because this fx is the distance, and if this beta is 1, then we can easily use this. So this beta is equal to 1, we will add as a constraint to avoid large betas, so that we should not penalize fx, okay. Secondly, just think about it. This normalization is to reduce the magnitude or to, some value to 1, the unit vector. But why it is only unit? We can go for any value. We can go for 2, we can go for 3, we can just use for scaling purposes. We are using it as unit vector, and here it is some m is there, so we will define beta in terms of m so that we can remove this m. So let's define beta as 1 by m. We are just using this beta 1 by m because m is an another variable which we don't know and we want to maximize, and it's just a scaling variable. So if we want to maximize m, it's similar that if we want to minimize 1 by m, or you know let's say if something is proportional, let's say height and weight are proportional, so if we want to increase the height, obviously the weight will be increased. So in either way we can have that. So we are now not using this constraint, the magnitude of this norm beta is 1, we will use this constraint, norm beta is 1 by m, and our main objective is to increase, maximize this m. So let me know if I want to write maximize m. So for 1 by m, can we write minimize? Yes or no? If I want to maximize m, is it equal to the minimization of 1 by m? Yes or no?
Yes.
Yes, ma'am.
Okay, so this 1 by m can be treated as beta. So this beta is written here. Plus, for some derivation purposes, we just take the square and introduce half here, so that the derivation of it is 2 beta, so that we can easily define the derivatives. Okay, because if it is simple beta, it will give you the derivative as 1. That's why we just introduce this beta square and put a half here, so that if you get the derivative here, so you will get 2 beta, and 2 will be cancelled out using this half, and half will not is not an extra parameter. If beta will be minimized, half beta will also minimize, so it's not a big deal. All right, so basically, if this is your major optimization problem where you want to maximize this distance, right? But what is the distance? You have not defined it. So that's why a constraint is here, that the distance is given as yi fxi greater than equal to 1, because m is reduced to 1 now, right? Because I have taken beta is 1 by m, that's why the whole equation is divided by beta, and here also it is like, if it is
Ma'am,
going
second line, ma'am, once equivalent optimization problem. Second line, minimum 1 by 2 beta.
uh, this one.
Yes, ma'am. Yes, ma'am. How it is?
Do you get this?
Yes, ma'am. Yes, ma'am.
Okay, so I want to maximize m. My question is this: I want to maximize m with constraint this was the constraint. Okay, now I am converting this m to beta. I am telling, if you want to maximize m, just minimize 1 by m. I can write it. Can I write? Just think about it. If I want to maximize m, matlab
Yeah.
I want from 10 to 100 to 1000 to 10,000. To minimize, it means this value will be minimized. If I increase the value of m, then 1 by m will be minimized. Okay, because it is in denominator. Okay, good. Chale aage. Okay, now I have, look, I have taken 1 by m na, so I will take here also 1 by m. So multiply by 1 by m here, multiply by 1 by m here. So 1 by m is more like, this will be cut it out and equal to 1. So that's why this constraint is 1, and here if you multiply it by 1 by m, it means 1 by m I am taking it as beta. So beta norm, if you will multiply it, then it is like, the norm of beta is already 1, so it doesn't affect it. So that's why we introduce this inequality, that subject to condition 1 here, because I have put it 1 by m. Initially it was m, I divide it by m. Here this 1 by m is written as beta, this beta, and if I want to minimize beta, then beta square will also minimize. Is it the same thing? because they are proportional. And if I put half in front of it, then it is also minimized, then it's not a big deal. It's okay.
Yes, ma'am. But how it is become right subject to why I
So
this line, ma'am?
it is written here. Okay, the subject to condition this distances should be greater than m, right?
M, yes.
So just divide it both side by m,
M,
or
yes, ma'am.
multiply it with 1 by m. So right side will be 1 and left
Okay.
side 1 by m is beta norm. Beta norm is already given as 1.
Yes, ma'am.
So that's why it doesn't affect it. So we have just used this one. Okay. All right. So geometric interpretation is more like we want to minimize this distance and we want to correctly classify the points. So it means if the points are here and some points are here, so these closest points, I am saying if the hyperplane is here, the distance, closest minimum distance will be 1 by beta. Okay, that is m. So these points are m distance apart, at least I'm saying. Okay, so the more the m is, it means your hyperplane is just in between, basically. So this what you were actually asking at the first slide, that you are getting confused. So using the same constraint, we are getting those 2 points, the maximization point plus, obviously because all points are considered here, the closest point, it means the value m is equidistant here. It means it is also m and it is also m. Okay. So
Got it.
now using this information, we introduce SVM. SVM is support vector machine. It's a supervised learning algorithm for classification as well as regression. So its main aim is to find the optimal hyperplane that maximize the margin. Okay, it works for high dimensional data as well. So I'm just going towards the optimization problem as we don't have much time. So basically same thing we are going to use as we have seen just now, because this now either I will use beta or w, it's the same thing. Okay, don't get confused here. So beta are also weights, w are also weights. So this is the same problem that we have written just now, but just the variables are changed from beta to w. It's the same thing that we have just discussed. Okay, so now this is to be solved. So look, this is the main optimization problem, this is the constraint. So when we have constraint, we go for Lagrange. So I'm not going into deeper details for optimization. So when you have the condition here and we are using some Lagrange variables for that, so that let's say this is fx, this is gx. Okay, so if gx is there, then we introduce a new problem like this. So I have given you some slides over Lagrange. Let's say that some fx is there, some gx is there. So Lagrange multiplier will be like fx is equal to this. It means your optimization is more like fx minus alpha या lambda जो भी a constant gx. Okay, now problem is changed to like this. And because some alpha is also introduced before your problem is related to beta and beta naught, now it is include alpha also. So this is the new problem using Lagrange multipliers if you have some constraint problems. Okay, but one thing, this gx should be like gx is equal to 0. So if it is something here, we have to move it towards the right hand side. So here you can see this one, yi fxi greater than 1, then we put the 1 to the left side. So we will get yi w transpose xi plus beta minus 1 is equal to 0 or greater than 0. So this constraint, this is called G. This is full G. So now this is fx, this is gx. So fx minus alpha gx will be your new problem, new optimization problem from Lagrange multipliers. So simple, I'm just actually
Ma'am,
setting this. Yes.
CFX minus.
Yes,
Ma'am, where is it? It is written fx minus gx.
this one. This is fx and it's
Okay,
called
okay.
gx. Okay.
Okay, okay.
Now you see that initially the problem is for w and beta. Okay, w means beta here and b means beta naught. I'm just using this notations. So basically this beta and beta naught, extra alpha is joined because alpha is introduced. Okay, so now the problem is same. Take the derivatives. So dl by dw, dl by d beta, you get some values. So from this, just you can use this because you can actually solve this. It's a simple derivation. You can easily solve that. When you derivate this L with respect to W and equate it to 0, you get the value of W is equal to something. Okay, simply you can get that. I'm not solving it for you, but you can solve that so that I can complete this lecture. Secondly, when you derivate it with respect to beta naught or B, you will get this value. Simply, it's not a big thing. Okay, but as you see that here also I get the value of W, I get the value of B. Can you see here what are the terms in W? Alpha, Y and Xi. Y and Xi you will know, but what about alpha? How to calculate alpha? Here also Yi is given, but what about alpha? You don't know the value of alpha. It's a question. Okay, so it means this equation is not completely enough to calculate the value of W and beta because it requires the value of alpha. Okay, so whenever we have this problem, this is the primal. If you know about optimization, this is the primal. Now we convert into dual so that we can get the optimal value of alpha. Again, listen, sometimes what happens is we have a problem with constraints. So to solve the problem, optimization problem with constraints, we use Lagrange multiplier. So for Lagrange formulation, we add one more parameter alpha. Now you have previous parameters, beta and beta naught, yeah, W and B, and now you have one more parameter alpha. So using this equation and solving out, we can have the value of W and beta, which is in terms of alpha, but we don't know the value of alpha. So because we can't simply calculate alpha, we calculate the dual of it so that we can easily calculate the value of alpha. Okay, so the dual says that you actually put the value of this W beta here in this equation and you will get this. Okay, I'll upload one handwritten notes again to solve this. So basically, when you put the value W, here W is written, so you will put the value summation I to n alpha I yi xi. Just put the value of W here also. Just put the value of W, B as alpha I yi. So all this equation is converted into the variable into alpha. Right? No W's are there, no betas are there, right? Because you get the values of betas from here. But to get the value of alpha, we have this equation and we form a dual because from the Lagrange multiplier, we say that alpha is always greater than 0. So we want to maximize alpha. Okay, so
After different partial differentiation, we got W equal to something this
yes,
value means
yes,
second
yes,
line.
yes.
Okay, okay.
ठीक है, we get this W, we get this B, but what about alpha? We don't get alpha na, we want to find the alpha value also. So what we will do, we will simply put this value of W here, we will put the beta value here. Okay, so when you put this value, you will get an equation like this when you solve it. I will share the handwritten notes, okay, in the drive, so that you can have that calculation also, but it is very easy to solve. It's just you have to put it and just this use this minus and all, and you will get that. So basically now this dual problem is to solve, get the value of this alpha. Now one thing note here, can you see here this is x into x? Yes or no?
Yeah, ma'am.
Yes, okay. So whenever you try to solve this problem and there are this, because this is alpha alpha, this is y. So it is leads to quadratic optimization problem. So it actually it should satisfy some condition also, and you can have the value of alpha using quadratic programming, which is not easy to solve here by manually handwritten. Okay, so generally when you have questions in books also we have tried, so it is used using programming. generally alpha values are given to you. Secondly, which I have not mentioned here, this KKT condition, you will have to find it out. What are these? Basically, when you are using this Lagrange dual problem, there is some condition by, this is called as Karush-Kuhn-Tucker. Okay, so they actually define some conditions that this condition should be satisfied. From those conditions, it is written as this value should be equal to 0. This is alpha I, yi, fxi. So alpha I, yi, fxi should be equal to 0. Okay, so I'm not going into KKT conditions. You have to find it out. All right, just take this as fact that from KKT condition we got this point. From this point, let us say I divide it into two things. So basically this yi is plus 1 or minus 1. Agreed? Yes or no? These yi can be plus 1 or minus 1. No value. All right. Is it true? Good to go? Okay. So basically this cannot be 0. So either alpha I be 0 or fxi be 0. There are only two conditions. So I am writing here as either alpha I will be 0 or this will be 0. Okay. So means minus 1 is also there obviously. So this will be 0. It means that this is simple. If this will be 0, take the 1 to this side. So it means this value. Okay. So it means that if this is equal to 1, it is meaning that these are the closest point. This 1 indicates here the maximum margin, right? The maximum margin we have reduced it to 1 because we have taken 1 by m. So basically I am saying these points are the closest point and these are called support vectors. So we can define support vectors where alpha I is greater than 0, not 0. If alpha is 0, alpha is 0 for the other vectors, but those are the support vectors will have alpha I is greater than 0. So if you have the values of alpha, you can have support vectors. Listen again. When we are getting this equation, we want to optimize it. We want to find the value of w and beta. We get the w and beta with the values of alpha I, yi, xi, alpha I, yi. So you need the value of alpha I, yi or xi. yi and xi will be given to you, but what will be the value of alpha? So according to KKT conditions, from this equation we are saying either alpha I is greater than 0 or equal to 0. So if the alpha is equal to 0, it means the point are behind the support vectors. It means other points which are not closest, which are farther from the boundary. And if alpha is greater than 0, means it has some value, it means it is on the support vectors. So for alpha I is equal to 0, this value will not be applicable. Obviously, the weights are sigma alpha I, yi and xi. If alpha is 0, then it will not contribute to w. So we can conclude that only support vectors will help you to found the marginal plane, this hyperplane. So these support vectors are those vectors where alpha I is greater than 0. And how to find the value of alpha I? Using quadratic programming, which is not into a major topic of interest right now. Okay, you can see it afterwards. It's a programming concept where you can find the solution of this equation using quadratic programming. You will get the value of alpha I. So I have one example related to this. Okay, I have written here course also. This is a book from Zaki. Zaki is the author, and
Ma'am, one second, go to the previous slide. Once.
okay, the book name is Data Mining. Yes, go ahead.
Okay, ma'am.
Okay, so let's say this is your data, this is your whole data. These are having 14 points. Using quadratic programming, it is given in the question from where I have taken it out. They have given you the alpha values like this. For the rest of the point, the alpha value is 0. So it means those are not support vectors. These are support vectors. First thing. So first thing, I am throwing you an observation where alpha I is greater than 0, it means they are support vectors. Where alpha I is equal to 0, they are not support vectors. Good to go? Is it clear? Is it clear? Yes or no? Okay. I
Okay.
think I think something is you are getting confused. Okay. So basically, simply from this data we can find W. So W is alpha I, xi, yi. You know xi is this. Yi is this. Alpha I is given by this quadratic programming. Just sum it up. Alpha I is this. Okay. Yi is plus 1 or minus 1. Okay. So it is showing by the sign. Okay. And your xi is written by this vector. So just calculate the sum of this and you will get W. So simply W can be calculated with these points. So for SVM, just look it out. This is a whole process is reduced to a single step, that if you have the value of alpha, you know the value of y and x, you can simply just with a single step, you can calculate W or betas. Okay, so it's easily calculated if you have the value of alpha. So major problem of SVM is to calculate alpha. Alpha is having the equation like sigma of alpha I, alpha j, yi, yj and xi, xj. So this xi, xj plays a very important role to calculate to help in quadratic programming. Okay, so how it will be helpful, we will see that. So is this the idea of SVM is clear? If you have any doubts, then please go ahead first.
Can you show the previous slide?
This one?
Yes. Can you once again tell how we need to calculate alpha, ma'am?
Alpha at this equation is to be
Yes.
solved. Okay, this equation. So this equation has, look, alpha, it means alpha square is here, right? So if you take the derivative with respect to alpha, you have some alphas here, but because you have this x y y here, alpha is also there, so you can't simply solve it. To solve this, we use quadratic programming. Quadratic programming, it's a stepwise procedure. You need some programming method for that. Okay, you will have some programming values after that. Because look, one thing I'm also throwing you out, just see here. Can you say here alpha I and alpha j? Can you see? Yes or no?
Yes.
So let's say,
Yes.
and I and j are going from 1 to n and 1 to n. Let's say I have 10 points. Okay. So alpha I and alpha j create a matrix of 10 cross 10. That's why it leads to quadratic programming. So each value of alpha is multiplied by other all values. So let's say this is alpha 1, alpha 1, alpha 2, alpha 3 and alpha n. Alpha 2, alpha 3. So can you get this whole matrix? Now this matrix is to be solved for this optimization. Getting my points? Are you getting my point?
Yes, ma'am.
Okay.
Yes.
So it means that
Is there is a t as a suffix of x? Is this transpose or something or what? It's a mistake.
actually by mistake it is written. It is x transpose
Okay.
x,
Okay.
because these are vectors. We will see that actually it should be more general. We can say that the inner product, x transpose x is one form of inner product. So we will
Okay.
talk about that also. So
Once time,
basically, yes,
ma'am, how we take the column A1, alpha 1, alpha 2, alpha 3.
this is why programming, it is given in the question. You can see that it is
No,
given in
ma'am,
the
in
question. Huh?
box which is made by you, ma'am. Scroll down, ma'am, scroll down.
This one?
Scroll down, ma'am.
This one?
Yes, ma'am. This box, ma'am. And then only value.
This one?
Yes, ma'am.
What I'm saying, just look at here. Here it is written alpha I, alpha j, I and j, and two submissions are there for j and for I. It is like this, alpha I, alpha j. Okay, so it means for each value of each point is to be multiplied by the other point, so it will create a matrix. Let's say I is equal to 1 to 3. Okay, so it means I is equal to alpha 1, alpha 2, alpha 3, j is equal to alpha 1, alpha 2, alpha 3. So alpha 1 into alpha 1 will be written here, alpha 1 into alpha 2 written here, alpha 1 into alpha 3 written here. It means like this.
Yes, ma'am. Yes,
Okay,
ma'am.
in other sense, if I say these many alpha values you wanted, so it means you want to derivate each alpha I, so it creates a lengthy process, complex process. That's why it is solved by programs. It's called as quadratic program. Okay.
Thank you, ma'am.
Okay, all right, so these are, if alphas are given to you, you can simply calculate W, and if you get the value of W, you can simply calculate beta. How you will calculate beta? You will calculate beta with the help of yi minus w, because you know that y is equal to w transpose x plus beta. So beta can be calculated as y minus w transpose x. You know w, you know x, you know y, just calculate beta and take the average. Okay, for all the points given here, for these only where the alpha values are given. Okay, all right, is that clear? It's simple process. Shall we go ahead?
Yes, ma'am.
Okay, so now problem is with the perceptron is I'm now giving you some terms because I can't complete all this in one go. It will be like if you have not gone through the lectures, it will be difficult to digest many equations right now. So main problem is, let's go with the problem directly. Okay, let's say this graph, I'll just discuss with this graph. So here are blue points and red points. Okay, some hyperplane is given there. All right, these are the support vector, this one and this one. For this, the support vector are this and this. Can you see this is the extra point, noisy point? Yes or no? According to you, the what you are saying to me, that maximize the distance and equidistance. If I take this as the closest point, then my classifier, the hyperplane is shifted towards this direction. Yes or no? Yes.
Yes.
Now that's what I am saying. I will introduce this thing later. This is called soft FCM, where we want to maximize the margin. But if I use this as the closest point, it will not give you maximum margin. So I want to choose such vectors which will maximize the margin as well. So if I choose this as a supporting vector, it will not maximize the margin. But if I choose these two vectors, it will maximize the margin. But yes, the problem is this will give you some misclassified data. Okay. So what I wanted, having said this, we want to introduce this in our objective function. So we want to reduce these misclassification. Instead, we want to maximize the margin. Okay, so as you go out of the boundary, if this value, this noisy vector is in between the plane and the class side, then it is less than 1, and if it is on the other side of the class, it is greater than 0. So I introduce a new variable xi. These are called xi's, you know, these terms, xi's, which helps you to identify which are the noisy points, which are the misclassified points. So here we are using some variables in the objective function to reduce them. Okay, so this is called soft margin, where you allow some of the points in between the margin. Okay, just think about it. If it is in between, uh, just give me one deduction. Okay, this is the noisy point. Okay, this one. But is this correctly classified or not? Yes or no? Let me know this thing. Is it correctly classified or not?
Yes.
Correctly classified.
Correctly classified, but it is not coming into the constraints which we have followed. Ki the distance between the closest point and the margin should be m, right, or 1 by beta. So this point does not support that constraint, but it is correctly classified. So that's why it is also giving us good classification, but we wanted the margin, right, which should maximize the support vector. It is not acting as the support vectors. So we are saying support vectors are like this and it is maximizing the margin, but this is allowable. So that's why we call this SVM as soft SVM, not hard SVM. So previously which we have done is hard SVM, now it is called soft SVM, in which we are allowing some of the points to come in between the margins, both these margins. Okay, so you can go through the equations. I am not going to go into deeper details. I have written all this in this PPT as well, and you have very good videos for that. Okay, so I am throwing one term also, that is kernel. So I give you this thing. One of you asked me that, ma'am, is this transpose which is written here there as alpha I alpha j, yi yj, and xi xj, this x transpose. Okay, this one. So this term x transpose x is dot product. Okay, it's dot product, and these types of things are known as inner product. So inner product is written like this, xi xj. So it means it's more like a function which you will define. All right, so here basically kernel means just think, I am giving you a intuition. You are sitting somewhere in your room, let's say some blue and red color toys are on the floor, are just just they are just throwing it out, and you can't have a good hyperplane in between them, so you can't distinguish them. And if I say that just make them hang in the air and give some height to one type of products and some low height to another type of products, can you have a simple hyperplane in 3D? You have some red and blue point scattered somewhere, you can't have a particular line on the floor, you can't draw a line. So what I am telling you, just move all those products in the air. It means you are adding some height to them, and add height such that the blue product heights are more than the red product height. Okay, so can you insert a cardboard in between them now in the 3D? Yes or no?
Yes.
Okay, so it means that what is not linearly separable in low dimension can be linearly separable in high dimension, right? I'm just giving you a simple example of a 2D to 3D. But if we are moving towards more dimensions, it means those dimensions like LDA you have used PCA. You are saying that if we change the perspective, right? If we change the perspective or we add some more dimensions, it can help you for linearly classification or regression purposes. So that is called a kernel trick. So it's more like, let's say you have a function in, just think about in mathematical terms, it's nothing if you are going from 2D to 3D. In 2D you have x1 and x2, okay, and you have to move to x1, x2 and x3. So just define what is x3. It's just like that. So when you are increasing your dimensions, you are defining one function for it. So let's say you want x4 also, define one function for x4, define one function for x5. So if you have multiple functions, you have a different dimension of spaces. Getting my point?
Is it something like more degree of freedom, ma'am?
Degree of freedom, I can't say about it. It's more like basis expansion.
Okay, basis expansion. Okay.
Yes, it is more like basis expansion. Okay, so here the kernels are written as phi I and phi j, because these are two different, like it is written as xi and xj. The dot product between them is also a type of kernel. Another type of kernel means the function of 1 into function of 2. This function you have to define. So for example, There can be linear function, polynomial function, radial basis, or sigmoid. I give you an example of polynomial function. Just think about it. There is a point that x is defined as 2D. It means the x is x1 and x2. X prime is also x1 prime and x2 prime. It means it is of 2D space. And I want to convert it into D dimension, D space. Okay. So that D space is to be defined as polynomial 2. Let's say I have polynomial kernel with degree 2. So what I will do, it is defined as this formula, this one. So the inner product plus c to the power of degree. So inner product I have to define. So how the inner product work is actually dependent how you are defining a function. Okay, it can be x transpose x. Okay, it is generally I say x transpose x. So here also what I am using, the inner product is x transpose x dash, another one. Okay, so if x transpose is written as x1 x2 and x dash is written as x1 prime x prime, this one. So it is like x1. Okay. It's more like this. So I am writing like this. Okay, so if I will expand it, I'll simply open this square, a square plus b square plus c square plus 2ab plus 2ac plus 2bc. Okay, it's a simple thing. And I have defined some basis expansion also. So it can be seen that if you expand the basis to 6 dimension, it is equal to this kernel trick. So basically kernels are the function which map a lower dimensional space to higher dimensional space. And in this SVM, because we are using this xi transpose xj, you can use any kernel function here. So this SVM has a benefit that it can use high dimensional data as well. Okay, so you can go through now this kernel trick. So basically it is the which kernel function. There are multiple kernel functions. Generally we use RBF because it has dimension of infinity. It has some Gaussian kernels are also there which have Gaussian formula. RBF means it's a dimension of infinity in the form of circle or so. Okay, so basically next topic was hinge laws. Hinge laws is very much similar. It's more like because you wanted when you have defined the optimal that optimization function, in which you have defined that the this value is always positive, it should not be negative. So it means that you are making a assumption that its value should not be negative, it's also be a positive value. And when you introduce the alpha plus something function beta, right? So if you just rearrange the equation, it will be like some ridge function. You can go through the videos, it is very clearly mentioned there. So it's more like the loss that introduced after that is called hinge loss. Why it is called hinge? Because it's more like this graph. So it is connected with this hinge, that's why it's called hinge loss. And it is more similar like a ridge regression, where you add some regularization parameter of beta over beta. So when you rearrange those equation from first term to second term, it will move towards this hinge loss function. And this is your last final topic. Basically in this week's lecture, important is what is perceptron, how the SVM is working, and this kernel things. Okay, so go through those things. I can't complete all those things here actually, but if you have
Ma'am,
any doubt, that go ahead.
ma'am, this is last lecture of this session by you.
No, in this week, the week has multiple topics now.
Yes, ma'am.
So for in those topics, we have perceptron, we have SVM, then we have soft SVM, then we have this kernel, and last is hinge loss. So three important topics are perceptron, SVM. If you know SVM, what is SVM, you can easily learn about soft SVM. It's not a very big thing. Kernel thing
Support.
is very important. Okay, and some questions, as I can't let you solve here, but I have given some explanation for some questions. Okay, So which I think that I should be mentioning it here. So it is more written here. Some, and these are the last questions are related to your programming. So the instructions are given to you. It's more like you can use the inbuilt libraries. So if you have any doubt, you can go ahead. Actually, SPM is quite a lengthy topic.
Ma'am, if we are learn from your session, we can able to track exam.
Uh, Actually, I don't know about exam. This PPTs are also based on your videos only, because I don't want to throw you a new term. You are also already having the videos, and those videos are perfectly defined. But sometimes, as a new learner, we don't know many things. Okay, so that's what I wanted to give you a glimpse in these lectures. Let's say you will not have these simple questions, okay, because when the videos were made, it's more like the conceptual thing first, then it is related to the numericals. But wherever I can put those numericals, I have put it here in my ppts. So these are just the extra material, okay. And obviously, lastly, because today's session is quite numerical,
Ma'am, one thing that
please share your feedback
Ma'am,
actually.
can you share these questions in your?
Yeah, these PPTs will be given to you. These are the
Okay,
PDFs.
sure.
Yeah. That's why I keep these questions with the answers. But because on the first session, and the feedback I received, that you wanted more on topics rather than the questions, because I think other sessions are handling some questions as well. So you can join those sessions. So I'm covering those lecture things, but
if if
I
we
can do one
talk
thing.
for lecture, then it is sufficient because sir is talking in English. So sir, this is not your lecture is very careful, ma'am.
No, look, everything is important, right? Topics are always important, but if you know how to solve question, it's also important. So
Ma'am,
I don't want to repeat what others are doing. That's why, according to your feedback, I am choosing this, mm, because it's more important to have an idea about the topics and hence have some extra material.
content will be should be the same, ma'am, in both countries.
Sorry?
Content will be same, ma'am. The sir which have been taught in portal
Uh,
and
Generally, I keep the terms as such, which sir used, because separate terms will make you confused. So I am
so
getting, actually, I am reading those lectures only. Okay.
so you need to see both sessions, sir and your own say.
Yes, you can do like this. If you have, means you can start with these slides or these sessions, then maybe many things I can't cover here, okay? Because he has cover more mathematical concept more clearly. So you can have maybe good idea uh, from them after getting some basic idea from these sessions. So it will help you. It's more like that.
No, ma'am, you also able to clarify our doubt, ma'am. Your
Yeah,
session
that's
also.
why I'm saying I'm just at the basic level. If you are going through these lectures easily, then it will be helpful to understand those lectures more easily. Okay.
Yes, your session also. Thank you, ma'am.
Okay, okay. Thank you so much. Please give your feedback here, because some sessions are more expensive. So, all right. Thank you so much. Any other doubts or feedback you can share, obviously.
Ma'am,
Yes.
ma'am, can you please suggest some ways or methods to prepare for the exam, ma'am?
Uh, Look, I don't know anything about how.
Ma'am, ma'am, most of the students here are currently studying or are doing their PG, ma'am. So, how to manage with those subjects that we are studying for our degree as well as this one?
Look, I don't know about exams, rather how the questions are going to be there. I have no idea personally, but I can suggest that if I am at your place, the lectures are quite easy to go, right? Uh, so just start with the topic and try to solve questions and have an idea how you can apply those concepts, right? Because these questions, and if I throw you one good term here, you have chat GPT right now. So this generative tool is very much important. I mean, it's a big boon for me if I am using it to create some questions for the related topic. So you can solve those questions, but don't depend fully on that, because it gives you sometimes the wrong answers. So you will be the one who will, if you have the algorithm, just take the help of it. Or you can, like I have given you one book here, Zaki, for SVM. When we have learned machine learning, we Bishop is a good book, uh, but I don't find any questions there. That's why Zaki is more appropriate in terms of questions. So these two questions I have kept it from Zaki. You can either go with that book also, but
Ma'am,
yes.
ma'am, actually, sometimes I'm not able to get time to watch all the lecture videos, ma'am. So how to manage that, ma'am? Like
Uh,
sometimes I
I
kind of
would
tend to skip when I.
look. I would say that if you are taking all the lectures week wise, na, it will be easy for you. Because if you are, but if you are pending, keeping it pending, then it will be difficult. I'm also doing my PG right now, actually, but I'm able to get the lectures week wise. I'm also looking at those lectures because I have learned machine learning some 2 years back, right? So I have to go through many concepts again also. Plus, to prepare the question, I have to go through that. So if you will be preparing this content in a week, then it's a good start. But if you keep your lectures pending, then I would say that you have to work more. I don't know.
Yes, ma'am. It's not that I want to keep it pending, ma'am. Sometimes I just don't have enough time and I feel very burnt out, ma'am.
Yeah.
Because I'm not able to concentrate if I click the video at that time. So I decide that let me watch this another day.
Uh, this happens with all of us actually. It's a common problem, and it's like how you deal, it's a personal way out. But look, if you are having the concepts clear now, means if you are getting these lectures also, these TAs lectures. In fact, I have seen some TAs are working for programming, some TAs are working for questions, these MCQ types, and my lectures are, that's why, according to your feedback, I'm keeping it for content. So if you are getting these lectures, maybe you have a good knowledge about the concepts, and if you are good at these concepts, then the lectures are more free to go. So when you will read them twice, then it will be easy for you. Maybe something which you will not able to understand at that time, you will get it right now. So it will take less time for you. And personal suggestion, I generally see those lecture at the speed of 1.5 or 2. So I don't, you can
Ma'am,
try
I
that
just
also.
question, ma'am.
Yeah. Thank you, ma'am.
Okay, okay, thank you so much.
I have one more
Okay,
question.
one more doubt, ma'am.
Yes, ma'am.
In the context of this perceptron learning, what is the meaning of L1 and L2?
L1, L2, where it was actually, wait a minute, let me go through my slides. Perceptron, what is L1 and L2?
Yeah,
Have I written somewhere L1 and L2? No, I have not written L1 and L2.
no, it was not written there,
Hmm.
but they've asked about L1 and L2 penalty terms, but
Oh,
I don't
okay,
remember
okay,
seeing that
okay,
for
okay,
the
okay, okay,
perceptron.
okay. L1 and L2, that
For
is
the
not what
perceptron, that equation we did not see. I don't remember seeing in that.
you are talking about L1 regularization and L2 regularization, right?
Yeah,
Yeah,
yes,
I.
for the perceptron.
But perceptron, I have not seen that question. Is it in your this time assignments?
This time's assignment, one programming has come like that. But we should know what L1 and L2 is if we have to do it. No?
L1 and L2, I didn't get that. Because it's not, for programming assignment, you have to write L1 and L2.
Yeah, they have asked about it, but I don't know what L1 because none of the lectures I was not able to see any formula for that.
Maybe we don't know. Means, let me see the questions. Okay, let me see and connect you back. Okay.
Similarly, what is the difference between a regular gradient descent and stochastic gradient descent?
Stochastic gradient descent and regularized gradient descent.
No, the gradient descent and stochastic gradient
Okay,
descent.
gradient descent is just a simple way that you are taking all the data at one time. Okay, stochastic means you are taking one by one sample. It means you are updating the
Okay,
weights
okay,
one
okay.
by one, and if you are taking all the weights and taking an average, then it is called simple gradient descent, vanilla. But and what
Which
is
is better actually? Which is better?
actually the better is mini batch. Mini batch means you are taking some chunks of data, not one, not
What is the
two.
advantage of each of this? What is the advantage of regular gradient descent and stochastic gradient
Look,
descent?
just think about it. If you are changing it at one sample, then obviously the noise you are taking into account, right? If the noisy vector comes into picture, you will change your hyperplane
Yeah,
again.
yeah, yeah. But if you're taking everything together, that effect will be less.
Yes, but if you are having much more classes, okay, and if you are taking much amount of data and the classes distribution are somehow biased, then it will be biased towards one class. Okay, so
Okay.
that's why we take a small amount of data. Take
I have a ma'am,
That's
called
called
out.
mini batch. Okay.
Okay, okay.
I have a ma'am, one awkward question, ma'am. Ma'am, you are teaching only here or only other places also, ma'am?
No, I'm actually pursuing PhD at IIT Roper.
Ma'am, as you have sent your YouTube link, so we can able to learn only 4 lecture. The
Yeah.
by week it will be added into your playlist. So in the other places you are also teaching. So tell me please.
No, no. I used to teach. I have had teaching experience of 3 years, but presently I'm completely into PhD.
Okay, sorry ma'am for this.
Okay,
Keep it. Thank you, ma'am.
okay, okay. Thank you so much. All right, let's meet the next
Thank you. Thank you.
next week. Till then, goodbye.